In what follows, I'm going to be referring to uncommon sense, largely in the context of encounters during learning or teaching with ideas that challenge our current thinking. In other words, they seem in opposition to our common sense view of the world. And uncommon sense can appear in thought, feeling, and action. And just to give a taste of what I mean by it, I've got an example here that will be familiar to anyone who's driven a car. And that's the first time we drive on a wet surface and experience an uncontrollable skid. Every atom of our common sense tells us to get out of danger, and so we steer out of the skid. That would be the commonsensical response. But the correct thing to do is to steer into the skid. That goes against our intuitive thought at that time, at that critical moment. Once we've steered into the skid, the car is stabilized, and then we can adjust our position on the road and carry on as before. That just gives a taste of what I mean by uncommon sense. Or another term for it is counterintuition. It goes against our gut feeling of what makes sense. Presentation is structured in this way. I'm going to first introduce the sigmoid curve or the S curve, which may be familiar with most people. I'm using this because it's a very useful way to visualize the rest of my presentation, which concerns looking at how research progresses from two different perspectives, two different creative perspectives, those identified by Kaufman and Bagetto. The first of which is the big C perspective, historical creativity, and the second one is personal pro-C creativity. And then I'm going to go on to suggest education, the process of learning and teaching, can actually be viewed as a research project. From that, I will introduce the idea of learning thresholds. These are encounters with what we call troublesome knowledge, and then I'll give one or two remedies for how we might get past these thresholds, because we can actually spend considerable time at a threshold or not even pass it. So here's an example of a typical S-curve. It represents anything that grows over time into an environment in which there is feedback that actually can moderate that growth. And it has three distinctive characteristics, the first of which is not clearly shown on this graph, but it's truncated. It's a very slow beginning, gradual growth, followed by what you can see on the graph, a rapid acceleration in growth, and then a plateauing or a maturity in the growth where it actually flattens out. This specific example is that of the growth of a sunflower in terms of its height over time. And the reason I've chosen this is because the title of the paper that presented that graph was actually about something quite different. And this was by Mayer, who gave the title Biologistic Growth, Technological Forecasting and Social Change. And in that paper, he suggested that the S-curve can actually be used in a totally different context to predict how technologies develop and how changes develop in society. Now, it's been widely known and actually applied even since the 1960s, the S-curve, with regard to following innovations, new innovations. So a company would invest more research on the S-curve of an existing product when they were aware of the fact that it was starting to bottom out or flatline in terms of its marketing potential. I've just applied this idea from studying the review of research in different areas, and you can see the same repeated pattern of these S-curves. So this is how research progresses in terms of the historical perspective, big C. And it looks, as before, like this. There is a slow beginning where perhaps a new development has appeared in an existing knowledge base, irrespective of the discipline, a new idea that could extend the knowledge base. Someone perhaps submits a paper describing that new theory, that new technology that's been applied to the research field, or a new methodology, and progress is now starting to take place. Other people will apply that published work, and if it results in progress within their particular area, then we see this rapid development, this rapid part of the growth curve. Because there is no theory of everything, eventually that new innovation, whether it's a methodology, technology, or theory, will reach a limit. Then there's usually a period where there is no particular progress in that field. There's always gaps to be filled in within the body of knowledge, but I'm looking at the the growth of the knowledge at its limit, but eventually a new theory will emerge, and an adoption of a new technology or a new methodology, and the curve starts off again. You can look at any sort of research discipline and find this sort of curve of development over a period of 20, 30 or more years, and it's quite a useful way of visualizing research. And as I suggested earlier, the curves could represent progress in research underpinned by a new discovery. Discoveries are never planned, they're always accidental, but they always result in growth in a particular area. It could be a new theory, new research methods, or new technology, all leading to the growth of the next curve. And that gap between the earlier curve and the next curve is commonly described as a disruption. There could be a delay before the next curve appears, and that depends on many factors, such as the arrival of discoveries. Again, as I said, they're always unpredictable. The number of people working in the field, the level of funding, etc. So that's what research looks like. I've got an example here of some real data just to illustrate it, and obviously it's not quite as smooth as that idealized set of curves. But here we can see on this graph certain points whereby there is a disruption. That's identified by the vertical lines that have appeared in 3 places there. And in actual fact, this is a graph of the world high jump record over time, over a span of 90 odd years. And I've identified there the 4 different ways of jumping over the bar that appeared that resulted in the bar being raised. And then this was followed by saturation because a limit had been reached. And the most interesting part of that curve is when Dick Fosbury did a very unusual thing and changed the rules about how you jump over a bar. All the earlier styles of jumping involved jumping over the bar in a forward direction. But Dick Fosbury jumped over the bar backwards, and this was a completely uncommon sense of the time. But of course, as soon as he attained a much higher jump, everyone else working in that discipline changed the way that they jumped, and the bar continued to be raised. And it's worth noting a quote from Sir Brendan Foster on this event of an encounter with uncommon sense. He said, as soon as Dick Fosbury had jumped over the bar the wrong way, the rest of the world's high jump athletes started practicing doing the high jump the wrong way. So it was described as the wrong way to jump. Uncommon sense. But in actual fact, it gave a huge benefit and advantage to Dick Fosbury at the time. So that gives you an example with real data of what I'm talking about. The disruptions between individual growth curves. But I'm more interested in the actual body of the curve rather than the transition from one curve to another. So I've already discussed how research progresses from the historical point of view. It's those idealized series of curves with disruptions in between them. But I'd like to now drill down to the fine detail within a particular curve and discuss the personal or the pro-C perspective. What does research progress look like from the individual's point of view, not from the historic record of that research? And it's very different. There's our historic growth curves. Let's now just hone in on a tiny section of one of those curves representing any kind of discipline and ask the question, what does research really look like? Starts off with a delay when the research question is being addressed and ideas are waiting to be found in order to make some progress with that research question. And an idea, of course, is a disruption. It's an unpredictable outcome from thinking about a challenge. It's a creative idea. This is followed by another delay whereby that idea is perhaps put into practice. Then there's another idea that might speed up the development of it, followed by another delay. And then there's the inevitable setback where things didn't quite work as planned. And so on and so on. And that's really, from the point of view of a researcher, what progress really looks like. And the historic graph is that average dotted line shown there. So let's just identify these different parts of this more digitized curve that is actually, in actual fact, you could argue is disruptions all the way, not just between growth curves. From the individual perspective, that is what it looks like. So, and we can identify the different features. We've got creative steps that progress the field of research. There are delays and there are setbacks that hold it back. So now I just want to shift the thinking a little more. And given what I've just talked about, it's worth investigating the nature of education. And I'm suggesting that education is a form of research. In other words, we are learning new skills and new knowledge. It's still creative, even if it's not new to the world. So this is more like small c creativity as we progress in learning a new subject. So there's our recorded history. I haven't shown the flattened part of the curve because that recorded history is available in publications, initially in academic journal publications, and then the knowledge is compressed into textbooks, which are of course used in teaching the subject. So to summarize, big historical creativity looks like a very smooth curve, which one could infer is a story of superhuman achievement, error-free predictability, and certainty. And that can give an impression to students learning a subject that everything just fell into place and happened instantly and was conducted by very clever people. But as we've just seen in that previous curve, it's simply not the case. It's disruptive all the way. There are mistakes, there are accidental discoveries, and so on. So as I said earlier, this compressed knowledge then becomes part of teaching programs for the next batch of undergraduates. I want to argue that the experience of the student is more like this second curve, the one that I described earlier, which is the curve of the personal perspective of a researcher. So when a student is studying, it's not a linear process. They have delays, they have insights, they have setbacks when they've misunderstood something. So from the perspective of the learner, the experience of grappling with new knowledge, story of accidental discovery, failures, delays, and insights, just like before. Now, I'm not suggesting it's a mirror image of the researcher's perspective that I showed earlier, but there are delays, there are setbacks, and there are insights in the learning process. These larger insights are commonly known as learning thresholds, and there was a lot of interest in learning thresholds in education some years ago, and there seems to be less published about it now, and I believe it's a really important concept to work with regard to improving both our teaching and our own learning. And let me just give a summary of some threshold characteristics. This is by the pioneers of this work, Mayer and Land, in the early 2000s. They described it as troublesome knowledge, but once you've passed threshold, you don't go back, and it's always transformational. Just to summarize, the compression of historical creativity, i.e. the curve at the top, that makes education efficient also excludes the very processes that generate understanding, because the student is reading what looks like that curve at the top, characterized by the quote, but they're actually experiencing a much bumpier ride in trying to understand it. So what I'm interested in is how you might surmount these thresholds. What strategies could you use to get past them? Because one can spend a lot of time there. And I've actually met teachers who, at a conference, most of them admitted to this, that when I asked them, have you ever taught anything you didn't fully understand yourself? I got a unanimous yes. This is a common thing. In other words, you can teach a subject without having crossed that threshold, but it won't give you the freedom to be able to teach it in ways that are now enable students to pass it without a lot of struggling. So that's just an interesting observation that I acquired one evening at an education conference many years ago. So I now want to talk about these thresholds in a bit more detail, and more importantly, how you might deal with them. This is the often cited paper on these thresholds given above there. And they, to summarize, Land et al. Describe threshold concepts as forms of troublesome knowledge. They appear to be counterintuitive, alien, or incoherent. They're inhibited by common sense or intuition, which is one of the reasons that we spend a lot of time there, because we still draw on our common sense to get past them. Reversing one's intuitive understanding can involve uncomfortable emotional repositioning. And just to give another quote, there is no simple passage in learning from easy to difficult. Mastery of a threshold concept often involves messy journeys back, forth, and across conceptual terrain. So I'd just like to finish off with, very briefly, with examples from 4 strategies for surmounting these thresholds. And of course, I'm not suggesting these are not in use in teaching and learning. Some more enlightened teachers apply these. Given the demands of the curriculum these days, one wonders how much time is available for students to be able to examine these different strategies and apply them themselves. So I'd just like to summarize each one of those with examples. First one is using something called scatter. Now, this is a topic I came across in a different context. Scatter is just a way of dealing with troublesome knowledge simply by using a variety of sources to inform your understanding. But different authors can describe a concept that one's struggling with in different ways, and that can help greatly in acquiring the understanding yourself. And even crossing disciplines and finding studies of that subject can actually be very useful. And I'll give an example of that in a minute. I just want to mention in passing, I encountered this term scatter from the studies of works by Idries Shah, where he was talking about the use of scatter not in mass education in the Middle East, but in a more common form of earlier education in the Arabic culture, where it was more like the master-disciple approach to education. And it was a practice whereby a student would learn to understand ideas that they were struggling with simply by a multi-impact approach. This particularly applied with stories, and I've given an example there of the amusing character Mullah Nasruddin, who is deeply counterintuitive character shown riding a donkey backwards here. So scatter was something familiar to me before I became aware of a more formal educational process known as cognitive flexibility theory that was developed in 1990, which basically says the same thing, that you can get past these thresholds by studying from a variety of sources. And one example from my own experience was when I was entering the tortured debate about what creativity is, the definition of creativity, which still continues today. And I was struggling to find my own voice in that debate. And I was applying scatter, I was looking at different sources. And I just came across this book, which was basically about creativity in human evolution and prehistory, edited by Stephen Mythen. But in there was a really helpful review for me by Margaret Bowden. And that's where I came across the idea of creativity being related to the transformation of conceptual spaces. And that really was my light bulb moment in trying to understand creativity. So that's one example. And I'll just mention in passing this book that's been published fairly recently called Range, How Generalists Triumph in a Specialized World. Although it doesn't literally refer to either scatter or cognitive flexibility theory, the taste of this book is a similar idea. So that's number one. The second way of crossing the threshold is to actually examine the historical context. Because, as I said earlier, a student can be daunted by reading a textbook because it looks like it's been put together by very bright people who never made any mistake. And as we know from the disruption all the way curve, that is simply not the case. That is what research looks like, and it has done throughout history. In order to get over that emotional block that can come from feeling daunted by these ideas, being the history of the development of the idea. I'd like to give an example here from physics. The wave equation is probably one of the most influential equations with regard to the development of modern technologies in various forms in the last century. This equation is derived from Maxwell's four equations shown there on the left. These are vector equations. And in the texts, the derivation from those four equations to give us the wave equation on the right is dispatched in about 6 or 7 lines of vector calculus. I would argue that in following that derivation, the student doesn't really get a conceptual understanding of that wave equation. They may learn a little bit more about vector calculus, but it doesn't give you a conceptual understanding. If we go into the history, it took over 20 years to derive the wave equation. In 1861, James Clerk Maxwell published a paper on physical lines of force. 4 years later, he also published another paper, A Dynamical Theory of the Electromagnetic Field. And there were actually 20 equations at that stage. From those many equations, he derived the wave equation. But it wasn't until 1880 when Oliver Heaviside completely reformulated Maxwell's equations, reduced them to 4, and showed that very succinct derivation of the wave equation. And my argument is by just getting a taste, even a brief taste of that historical perspective can actually help the student in assimilating these ideas and dealing with the underpinning concepts. They don't have to study this in depth, but I just think it enhances that dry mathematical approach to teaching. I've just given an example from physics, but there are many other examples from different fields. I'm not going to go into the detail of those, but there's 7 different disciplines, all of which teach ideas let's say, in the course of a single lecture that are hugely compressed versions of what happened in history, sometimes spanning tens or even hundreds of years. And they're all reduced down to very simple ideas. And I really feel that the student misses out in terms of their deeper understanding by not being party to some of the history that led up to the development of those ideas. The third strategy for crossing the threshold is in widespread use, but it's still worth reiterating, and that's the development of teaching analogies. But analogies are a double-edged sword. They can be very useful in getting a picture by drawing on some area in life that we do understand well in order to teach us something that we don't understand so well, but they have limitations. And I'd like to give you an example from physics. In the early days of trying to understand the flow of electricity, an analogy that is often used is that of a water hose. And you can even find analogues for the voltage related to the pressure of the water, the current, the rate at which the water is flowing down the hose pipe, and the resistance related to the characteristic shape of the hose and anything that it encounters on the way. Very useful analogy for understanding the flow of electrons. But if we want to dive a bit deeper, that analogy breaks down. It doesn't resemble anything closely to what's really happening, and we need another analogy. So in actual fact, if we look at a microscopic level, the electrons actually drift down the copper wire, nothing like as fast as we would imagine, and they drift because they collide with the much larger copper atoms, bounce off them like billiard balls, scatter off them, sometimes going in the opposite direction, then recovering the direction, driven by the field that causes a net drift towards the positive electrode. Using the water hose simply doesn't apply here. We need a different analogy. And in actual fact, something like a pinball machine would be a great way of describing it. So this is just the caveat about using analogy. The water hose analogy must be discarded in order to gain a deeper understanding of how electrons flow. If anyone's interested in the development of analogies and some real evidence for their effectiveness, the reference below shows some really good working examples of how analogies were applied and improved the teaching, particularly of concrete thinkers. It's an excellent paper to study from the point of view of analogies for improving our ability to get past thresholds of knowledge. And my final example is simply, I've called shifting attention between creative and critical inquiry. And I just want to challenge some of the thinking, how we define, in particular, critical thinking. It's often listed like this. It's about analysis, reasoning, evaluating, inferring, predicting, synthesizing, and so on. And I'd like to argue none of those techniques are entirely related to critical thinking. All of our thinking is a sort of a jockeying between creative and critical inquiry in a rather randomized way. So critical thinking concerns logical solutions, reasons, and creativity concerns idea, intuition, and imagination. And if we look at the history of critical thinking, it was initially called convergent thinking by Guilford in 1950, where we draw conclusions from knowledge available to us at the time, symbolized by the convex lens there. In a more modern context, Kahneman has identified this as system 2 thinking in his book Thinking Fast and Slow. With regard to creativity, Guilford referred to this as divergent thinking, where we need to go out into the unknown, symbolized by the diverging lens there, in order to gain new ideas. And Kahneman identified that as system 1 thinking, that whenever we're problem solving, we randomly switch between creative thinking and critical thinking. We can put a greater emphasis on creativity willfully or a greater emphasis on critical thinking, but ultimately we are at a micro level, randomly oscillate between the two. But let me just give you an example of what would happen if we tried to solve a problem only using critical thinking or logical solutions or reasoning. And I'm going to give an example that should be familiar to most people in the area of mathematics. So let's just see how we might solve this problem using reasoning alone. And I'm using here the well-known, the general solution to the quadratic equation, something we learn at high school. Often in the textbooks, we get this phrase, it may be easily shown that ... and we can arrive at the conclusion, which is the general solution, just by applying reason. Well, it's simply not the case. There's a big gap on the way to finding that general solution, and that gap needs a creative insight. And that insight is a technique called completing the square. If you're not familiar with that technique, it's highly unlikely you will actually arrive at that solution. Again, reasoning alone will not solve problems. We need to jump between creativity and critical thinking to get a solution. What if we approached a problem just using intuition and no reasoning? Well, here's an example. If I have a wet sponge and it's 99% water by weight, and I squeeze out some of the water so that it's 98% water by weight, what percentage of water has been squeezed out? Well, if we just look at that intuitively, it would be a reasonable conclusion to say, well, 1%. We just subtracted those two numbers. But this is wrong. And in actual fact, we have to apply some logic or reasoning to get the correct solution. And that logic is to say, let us assume the wet sponge weighs 100 grams. Once you start off with that, doesn't matter what weight you assume, you can then come to the rather surprising conclusion that the amount of water that's squeezed out is about 50%. And that goes against our intuitive beliefs. That is the final strategy I would suggest for helping us navigate those thresholds, those learning thresholds. So in conclusion, I have demonstrated the use of the sigmoid curve for visualizing creativity from a historic point of view and also from the professional experience, and related this into the context of teaching and learning. And within that context, I identified what thresholds look like and identified methods that can be used by both the learner and the teacher to get past those counterintuitive thresholds. So thank you very much for your attention. If anyone has any questions, I'd be happy to answer them by email using the address given below. Thank you.